All right. Are we doing SAT stuff today?
No, I think we're gonna prep for my test.
Okay, that's absolutely fine. I wasn't sure when your final was, so I didn't know what we'd be doing today.
Yeah, it's on Tuesday.
Okay. So everything prior to Tuesday will probably be prepping for your final.
Yes.
All right. These problems you can verbalize?
Uh, Hopefully.
Well, if you can't, if they're like graphical in nature and you need to send a picture to me, you can do that.
Okay. All right, let's go to. Do you know anything about um like sound waves? Like that's part of what I need to learn. Logarithms having to do with sound waves.
I know a lot about logarithms. I'm not sure I can connect them to sound waves, but I definitely understand logarithms and exponential functions.
Let me go to it. Well, okay. Let's focus on the laws of logarithms and
Okay.
things like that
Okay.
because I have trouble with that.
Okay. Here, let me write the three most important laws of logarithms.
Okay.
The log of a times b is equal to the log of a plus the log of b. That's number one. Number
Okay.
two, the log of a divided by b is equal to the log of a minus the log of b. And finally, the third really important one is the log of a to the b power equals b times the log of a. And this might be the most important one of all.
Okay.
Okay? So, and you want to be able to go both ways on this. In other words, when I go this way, it's called expanding the logarithm. But
Okay.
when I condense it, I'm going this way. So if I said I've got the log of 3 plus the log of 4, it's going to be the same as the log of 3 times 4, 12.
Right.
Okay.
Log 12.
Uh-huh. And you can get each of these out of your calculator, but you'll find that this is true. But it's the property of logs that's important, because at some point you use variables here, and then you have log equations, and you have to solve log equations. So do you have some specific log problems we can do?
I'm trying to look for them. Let me go to the back of the book. No, it's the front of the book.
Usually, anything with logs, there's usually a section of problems where it says expand them,
Mm-hmm.
and then there's a section of problems that it says condense them. In other words, if I told you to expand this expression, that would be the log of x plus the log of y. And
Right.
incidentally, these rules on logs only apply if you're talking same base. In other words, these three rules apply no matter what base is involved as long as it's the same. In other words, you can't say the log base 5 of AB equals the log base 7 of A plus log base 9 of B.
You have to use the log the formula to get them to the same log, right?
Well, there's the change of base formula, which
Right.
says the log base B of A equals the log of the top number divided by the log of the bottom number. And it turns out that this is the same regardless of the base. In other words, that's the same as the natural log of A over the natural log of B. which is
Right.
the same as the log base 17 of A divided by the log base 17 of B. In other words, these ratios are all the same even though they're different bases.
Okay.
Okay. It's not really that often that you have to use the change of base formula. If you kind of learn to work with natural log all the time, then you will almost never have to use change of base formula. Unless they specifically give you a problem that says, you know, what is the log base 7 of 8, then you would have to use it. But usually everything's going to be in either common logs or natural log. And once you get to calculus, natural log is the natural.
Okay.
Once you get to calculus, you almost use nothing but natural logs. And it's because
So now mostly
natural log
everything
has
is
such a nice property in calculus.
right now everything is log of 10.
Common logs. Okay.
Okay, so I have one.
Okay.
It says sketch the graph of each function and state its domain, range, and asymptote.
Okay.
So it's g of x equals log base 3 times the quantity 10 plus, x plus 3.
Sorry, what's the argument again?
X plus 3.
X plus 3?
Yes.
First of all, let's talk about the domain. You cannot take logs of negative numbers. You also cannot take logs of 0. It has to be a positive number. It doesn't make any sense to do this. Can't do it. It's kind of like taking the square root of a negative number. Okay?
Just
results in imaginary solutions is what it does. So the very first thing we need to know about domain is that whatever the argument is has to be greater than 0. Not greater than or equal to, but greater than 0.
okay.
Which means if I solve this inequality, x has to be greater than minus 3. There's your domain.
Okay.
And it's not a function of the base. The fact that this base is 3 is immaterial in terms of domain.
Okay.
Okay? Now let's talk about graphing it. If I graph the natural log function, it looks like that. Okay? In other words, that would be y equal natural, we'll even say log base 3. And now let's talk natural log. Okay? That's what that curve is. And it goes through a specific point that is 1, 0. Okay?
All natural logs?
What's that?
All natural logs?
All logs do.
Okay.
In other words, it doesn't matter whether it's, excuse me, I meant to write natural log of x, but whether I'm graphing natural log of x or log base 3 of x or common log of x, they're going to look just slightly different from one another. In other words, maybe the blue line is y equal log of x. And maybe I have another line that is y equal log base 3 of x. Every one of these functions goes through this point, 1, 0. In other words, the log of 1 is 0. The natural log of 1 is 0. The common log of 1 is 0. The log base 3 of 1 is 0. All of those are true.
Okay.
So each of these three functions that I graphed look very similar. If I were to erase the other two, you'd have a hard time telling which was which, because the key point they go through is all the same, 1, 0.
Okay.
Okay, so I'm going to erase two of them. And the one I'm going to leave up there is going to be y equal log base 3 of x. Well, that's very similar to the problem you gave me. How does it differ? In other words, talk about this as the parent function and talk about this as being translated. In other words, log base 3 of x plus 3 is merely translated from log base 3 of x. So if we can figure out the translation, we can graph it very easily.
Okay.
What is the translation? If you remember from your translations and reflections, what's the difference between this one and this one?
The difference.
What does the top one have going on that's different?
Plus 3.
Okay, and what is that? That is a horizontal shift
Okay.
to the left of 3 units. Okay, so I'm going to take my red graph that represents log base 3 of x, and I'm going to shift it 3 units to the left. Well, the one point that I know is on there is 1, 0, so that now becomes minus 2, 0. And I basically have a graph that looks almost parallel to it, and it has a vertical asymptote at x equal minus 3. Notice that when x is equal to minus 3, we would be taking the log of 0, which we cannot do. It's kind of like division by 0. When you have division by 0, you have a vertical asymptote on the graph. Well, when you have the log, whatever the argument, where that's equal to 0, you're going to have a vertical asymptote. Okay? So everything in blue is the graph of this function at the top. Its domain is x is greater than negative 3. And you can see that from looking at it. In other words, if you were looking at nothing but the blue graph, you would say the domain, well, x has to be greater than 3. It goes from negative 3 to infinity.
Okay.
Okay. The range, I know they didn't ask you this, but the range is negative infinity to positive infinity. In other words, clearly the blue line goes all the way to negative infinity. It keeps getting closer and closer to that vertical asymptote. And even though it looks like it flattens off here, it really doesn't. It keeps going up and up and up and up. So that as x goes to infinity, g of x also goes to infinity.
Okay. If I wanted to graph that on like a graphing calculator, is there a way to do that?
Yeah. Depends on which graphing calculator you have.
I have the TI-84.
You can certainly graph the log of x plus 3 or the natural log of x plus 3. Whether you can graph the log base 3 of x plus 3, I don't know. I used to have a virtual TI-84 on my computer until I upgraded, and I don't have it anymore. And my TI-84 is not operational, so I can't try it. But where you would graph it would be to go into your y screen where you define your y functions that you're going to graph. and type log. I don't know how you put the base in there. But it would be log parentheses x plus 3. That would be the common log of x plus 3. And it's going to look almost exactly the same as the one I drew. You're not going to be able to tell the difference.
Okay.
Whether they have a way of putting in a base other than 10 or e, I'm not sure.
But doesn't that not actually matter when you're graphing it?
Well, it matters. In other words, if the blue line I've drawn, if that's log base 3 of x plus 3, then natural log of x plus 3 is not going to look exactly the same. It won't be on top of it, but it'll be close. You wouldn't be able to tell the difference between them if I showed you one versus the other. So it's going to have a very similar shape. All log functions are going to have this shape that I've drawn here. And they are all going to be asymptotic with the vertical asymptote.
Okay.
Okay. I could go into Wolfram Alpha if you like and graph it. Here, let me see.
No, because I just got a graphing calculator and I know that I just wasn't sure how to graph on it.
Well, what I need to do that I haven't done yet is re-download the virtual TI-84 that is available for free online, and then I can bring it up on my screen and I can show you exactly how to do stuff on that calculator. I just haven't done it and don't really, can't do it during our session. It takes a few minutes to download. It's really a nifty program. It's like having a TI-84 on your computer.
Yeah. I think I just got it to graph it. I mean, it's at least really similar.
Well, were you able to put in the base of 3?
No.
Then you're probably looking at the common log of x.
Yeah, it is the common log.
Yeah. Like I said, I'm sure you can do common log and you could do natural log by just spelling it ln.
Yeah, and ln would probably be closer, wouldn't it?
Well, yeah, because e is 2.71. So the natural log of x plus 3 is going to look very, very similar to the log base 3.
Right, that's
More so than the log base 10.
Right.
But they all are going to have the same shape, and they're all going to go through that same point, -2, 0. So the only difference in them would be one might be vertically stretched a little bit relative to the other, but not so much that you could tell the difference by looking at it.
Okay.
There's probably a way to put a different base in there. Just can't imagine what it would be, really. I'm sure the Inspire allows it, but the TI-84, I'm not positive whether it does or not. It might not. It's kind of like, you know, the TI-84 only has 2 keys. It has a log key, which is common log, and it has an ln key, which is natural log.
Right.
If you want to do anything with a base other than those 2, you have to use the change of base formula. Ah, that's exactly how you would graph this. Graph it as the log of x plus 3 divided by the log of 3. In other words, in your calculator, use the change of base formula. Well, the change of base formula says this is the log of x plus 3 divided by the log of 3. So put that in for your function, and then you would have the log base 3 of x plus 3.
Log x plus 3 divided by log of 3.
Mm-hmm. That should give you something very similar looking to what you had.
So negative 0.1243. And then what do I do with that? Do I graph that?
You shouldn't have gotten an answer, not if you had x. In other words, you had a variable in there.
Yeah.
You had the log of x plus 3, all in parentheses.
Wait, when you're using the calculator, x, the variable is just the letter x, right? Like the alpha x?
No, there's a key on that TI-84 that it's, hold on a second, let me get mine. It doesn't turn on, but I can still see the keys. You see the key that says xt theta n?
Yeah.
That's the key you want to hit when you want to put in a variable.
Log x plus 3.
Make sure you have parentheses around the x plus 3.
Yeah. Log 3. I still got an answer.
Well, you shouldn't, because you got a variable in there. How can you get an answer? It's going to be dependent on what x is. I don't... It's going to be hard for me to help you with this until I can get that calculator downloaded to my computer. If you want, I'll make a note of it, and the next session we have, I'll have one on there, and I can help you with calculator stuff. Okay? Yeah. Because it's awful hard to describe and explain how to use the calculator without having it available to us. And I can't be positive of what you're hitting or anything until I can show you a virtual keypad for the TI-84 that actually lets you hit the keys and do exactly what you're doing.
Okay.
So I'll make a note.
So
Download TI-84. Okay. What else can we talk about?
This says 6 to the 2x equals 25, and it says write that in logarithmic form.
Okay. Let's talk about logs first of all. Every discussion on logs really needs to begin with this. That is an exponential equation. It's not an algebraic equation. We can't solve it algebraically. An example of this equation might be 8 equals 2 cubed. Okay? Now, every exponential expression has an equivalent logarithmic expression. So if I want to express this logarithmically, I only have to remember one thing. Logs are what? One word. Logs are exponents. Okay, so if I'm trying to write this as a logarithmic expression, the very first thing I can write is the log has to be equal to x, because logs are exponents.
Okay.
Well now, where do the b and the y go? The b always goes down there. The only place left for the y is there. Okay, now let me take this expression over here and write it logarithmically, or you do it for me.
So log of 3.
Well, when you're verbally talking about logs, say log base something of something equals something.
Okay, log base 2 equal this is times something? Oh, right.
Of 8, and it's not times, equals 3. In other words, when I write this, I do not mean the log times 8. It's a lot like saying f of x. That does not mean f times x. It means
Right.
f of x. Okay, this means the log of 8. Doesn't mean the log times 8. That wouldn't have any meaning all by itself. In other words, log always has to have a base and an argument. Well, if I write it like that, the base is assumed to be 10, so I'm saying the log base 10 of 8 is equal to what? Well, then I would have to solve that. So before you can solve or convert any problems, you have to understand this right here. And you have to be able to go in either direction. So let me give you some problems. Write that as a logarithmic expression.
Log base 2 of 16 equals 4.
Okay, good. Now notice that if somebody gave me the logarithmic expression, I could always convert it to the exponential expression by taking the number on the far left, raising it to the power of the number on the far right. That equals the number in the middle. In other words, 2 to the 4th equals 16.
And you can just switch those out whenever you want?
Well, you have to be able to go back and forth. In other words, you have to be able to take a logarithmic expression and convert it to an exponential and vice versa.
Okay.
So let's take the problem you gave me. 6 to the 2x equals 25. We do not have algebra that can solve this. This can only be solved using logarithms because this is an exponential expression over here.
Okay.
Not an algebraic expression. Okay.
So you got to put it to logarithmic form. Matt?
What I'm going to do to solve all exponential equations is to take the log of both sides. And I basically have a lot of choices here. I could take the log base 6 of both sides, but it actually almost makes more sense to just always use natural log or common log. And I'll show you why. If I take the natural log of both sides, which I can always do because you can do anything to one side of an equation as long as you do it to another. And that includes all kinds of processes like logs, derivatives, limits, integrals, all kinds of things. I can square one side as long as I square the other. Okay. Now, using the logs of the properties of logs, remember what that third property was? It was the log of a to the b power is equal to b times the log of a. Well, you can apply that property on the left side here. In other words,
Wait, so
it was the log of a to the b power equals, you bring the b down and it's a multiplier, like that.
Okay.
So on the left, whenever you have an exponent, once you have it into a logarithmic expression, you can bring this exponent down on the algebra line. So now it becomes this. Now it's an algebraic expression, and I can use algebra to solve it. In other words, 2x is going to equal to the natural log of 25, which is just a number, divided by 6. Then I'm going to divide both sides by 2 to get x, and there's what x is. Now, I can change that a little bit even. I can take that 2 and make it an exponent. So that's going to be the natural log of 25 divided by the natural log of 6 squared, which is 36. So that is my answer. Now, that is the most precise answer you can get. I could convert it to a decimal, but that's going to be an approximation. Logs are like all irrational numbers. They go on forever without repeating. So there's no way I can represent that number with a fraction. So if I want the most precision, my answer is natural log of 25 over natural log of 36.
and they don't cancel.
They do not. And furthermore, let's go back a moment. And there's another way to do this problem that maybe your teacher would teach you, which is instead of taking the natural log of both sides, let's take the log base 6 of both sides. Which seems right because when I take the log base 6 of 6 to some exponent, it's equal to that exponent. In other words, this part of it's always 1.
Okay.
Okay.
Right.
So now I have 2x equals the log base 6 of 25, and then I can divide both sides by 2 to get x. But so this would be your answer, but notice that I can't get that out of a calculator, certainly not your TI-84. You can out of an Inspire, but your TI-84 requires you to use the change of base formula.
Right.
So this would become the log of 25 divided by the log of 6. I still have to divide by 2. So I end up with the same answer. I get log of 25 divided by the log of 36. And notice that that ratio is identical to this ratio. Doesn't matter if it's natural log or common log or log base 17. When you have ratios like this, they're all the same.
Okay.
Okay? And
therefore,
because you had to use the change of base formula, it was not really easier to take the natural or to take the log base 6 of both sides. It did not save a step like it appears like it did.
Right.
And because of that, I don't ever fool with those base 6s if I don't have to. You just use natural log. Once you start doing calculus and you get used to it, natural log is the log du jour. It's the log of choice. I could also have taken the common log of both sides. But then the common log of 6 is not 2x. It does allow me to bring the 2x down and stick it in front, so I can still solve for x, but I get something that's in term of natural log instead of, or rather common log instead of natural log.
But why does it matter between log and natural log?
It doesn't.
Okay.
You could do either of those, but I get the same thing. Watch. Okay, I'm taking common log of both sides. Now I have this. Common log of 6 equals that. Now I divide by common log of 6 and the 2. So I get x equals that. Well, that's log of 25 divided by log of 6 squared, or 36. So it's that ratio. Well, guess what? That's the same as the ratio I got when I used natural log. Natural log of 25 divided by natural log of 36 is the same ratio as common log of 25 divided by common log of 36. So it didn't matter. The only thing that really kind of matters is stick with common logs and natural logs when you're solving these exponential equations. Then you will never have to deal with change of base. Well, I shouldn't say never. You may get a problem where, here, change the base. But when you're solving exponential equations like this, just always work with either common log or natural log, and I would choose natural log always because it's the log of calculus, and that's where you're headed.
Okay.
Got another problem?
So let's do another one kind of like that. Log of, wait, let me write it out. Log of, no, log base 2 of 80 minus log base 2 of 10. Isn't that just log base 2, 80 times 10?
80 divided by 10.
Oh, divided, right.
In other words, you are going to use the logs, the rules of logs to compress this to one log expression. So that is
log
named log base 2 of 80 divided by 10, which is 8. So that's the log of 8.
Which is 3, right?
Right. In other words, if I say, what is this equal to? Well, I would make up a variable. Now I would say, well, 2 to the x equals 8. What is x? X is 3. So the log base 2 of 8 is 3.
Okay.
And notice how I solved it. In other words, some you can solve without a calculator. You don't need a calculator for all logs. If they're whole numbers, you can frequently solve them without a calculator. But I didn't know how to solve that until I converted it to its exponential form. I had to do this before I could solve it. Let me give you another one. What is the common log of 1,000? What's that equal to?
Like you want me to express it?
Well, I want you to figure out what's that going to be equal to?
3.
Exactly. In other words, the base is 10.
Right.
I'm going to say, let's let it equal x. And now how do I solve that? Well, it's 10 to the x equals 1,000, and that I can solve. I know 10 cubed is equal to 1,000. So some log expressions you're going to be able to solve without a calculator.
Right.
Like this top one. In other words, that turned into the log base 2 of 8, which we were able to solve. That's equal to 3.
Log base 6 of 4 plus log base 6 of 9. That's log base 6 of 4 times 9.
Correct. That's log base 6 of 36.
Which is 2.
Correct. Now, you can only use these rules for logs if it's the same base. If that were base 5 instead of base 6, I could do nothing with it. No way I can compress those into one log expression. It's the same base, I can, but different base, I cannot. So every problem you get, it's going to be the same base. Never seen a log problem that was different bases.
This one looks more complicated.
Okay.
Log, and then it's a big radical, and it's a 3 root. There's no parenthesis. I don't think it matters.
Okay.
But, and then it's x plus 2 over x to the 4th times the quantity x squared plus 4.
Like that? Everything under the radical sign?
Yes, everything.
Okay. First of all, let's rewrite it without a radical sign. Because we don't know what to do with radical signs. We do know what to do with exponents. So let's put that to the 1/3 power. That's what the cube root means.
Right.
Okay. Now, I have something I can do with that 1/3. The laws of logs allow me to write that exponent and put it in here, like that. Same thing, exactly.
Wait, what?
I can take I can take the exponent that I had and bring it in front and put it in front of the log. You know what I'm talking about?
Yes.
Okay. In other words, that is equal to 1/3 log of that whole expression.
Right.
Okay. Now, let's break apart the expression. In other words, this is an expansion problem. Okay? So it's going to be 1/3. All of this is being taken to the 1/3, so I'm going to put the 1/3 in front of each part of this. Well, it's the top minus the bottom. Right? In other words, that's what gives you division, is when you have the top minus. Now, here, what goes in that is going to be x to the 4th. Well, actually, might as well multiply those together and make it x to the 6th plus 4x to the 4th, like that.
Okay.
Time. Oh, no, I multiplied it out already. And that's as good as we can do, I think. I don't see any way I can do any more on that.
So that's it?
Yeah, in other words, I've expanded it, and I have a numerator and I have a denominator. So it's the log of the numerator minus the log of the denominator.
Okay.
Now, when I have addition taking place inside the argument, I can't do anything. If I had multiplication, I could separate that into two log statements.
Right.
And I did start with multiplication, so I actually could have said log of x to the 4th plus log of x squared plus 4. I chose to distribute that first, but there is another way that this could be written. In other words, I could have written it like this. And then I'm going to subtract the entire 1/3 log of x to the 4th plus 1/3 log of x squared plus 4.
Is that what I should have done?
What's that?
Is that what I should have done?
Perhaps, yeah. If it's a full expansion problem, you could have done that, and then I can even do more. I can take this 4 right here and make it 4/3. So I can expand it even further. Here, let's do that. Let's make that 4/3 instead of that. And I don't have any exponent here. I have this 2, but that's an exponent of the x only, not the 4. So I can't do anything with that 2. And I can remove the brackets, distribute the negative sign. So there is perhaps the answer they would be looking for.
And then you remove the, okay. So
no, I've removed everything.
Yeah.
In other words, I kind of need these parentheses because that includes, in other words, if I write log of x plus 2, it's different than the log of the quantity x plus 2.
Right, of course.
So the only thing I did was I took the x to the 4th and I made it a multiplier of the middle term here, which you want to do when you're expanding a log expression. Kind of depends on whether you're expanding a log expression or if you're condensing one. Clearly, with this complicated looking one, we're going to expand it. We're not going to condense it. You condense, when you have multiple log expressions, you condense them when you want to make it into one log expression.
Like this one.
Yeah. Well, no, this was an expansion problem.
No, I mean this next one.
Okay. Go ahead.
x minus 2 natural log of the quantity x squared plus 1 plus parentheses, close parentheses, plus 1/2 natural log of the quantity 3 minus x to the 4th.
All right. Is this exactly the way it reads?
Yeah.
Okay. So this is a compression. Okay.
Right.
So the first thing I'm going to do in a compression is rule 3. I'm going to take this 2 and make it an exponent. I'm going to take this 1/2 and make it an exponent. So it becomes this. Okay, you with me?
Yeah. I'm just writing it.
Okay. Now I'm going to take this and combine it because I have natural log of something plus natural log of something else. That means I can turn it into a natural log of this something times this something. So it's going to be x minus, it's going to be a single natural log expression, and it's going to be multiplication because those were being added. So
X squared plus 1 squared times 3 minus x to the 4th to the 1/2.
Exactly. And that's
And is that as condensed as we get?
That's as much as you can do. Yeah, I mean, I could expand that, but I can't expand that. In other words, I don't know how to take the square root of 3 minus x to the 4th. I certainly know how to square x squared plus 1, and I could do so. So if there's anything more that can be done, I can square this, but it doesn't look like I can simplify it. In other words, once I square that, I'm not going to have anything that resembles this. Bless you.
Thank you. Okay. We have time for like one more, right?
Yeah, just barely.
Solution of the equation correct.
This is good. Log equations, let's go through at least one of them because there's something about them you need to know. Go ahead and give me one.
2 to the x minus 1.
I'm sorry, what?
2 to the x minus 1 equals 10.
Okay. Again, I don't have any algebra that allows me to solve this. But I can solve it with logs. Take the log of both sides. In other words, whenever you have an exponential expression, the solution lies in taking the log of both sides. Okay.
Right.
Now use your rules of exponents. What's the left side become? Or use your rules of logs, rather.
1 ln of 2 equals natural log of 10.
Okay. We're trying to solve for x. What's the next step?
Next step is to divide by natural log of 2.
Uh-huh. And finally, the last step.
X minus 1 equals natural log of 10 over natural log of 2.
Plus 1. If I'm solving for x.
And you can leave it like that, or should I actually?
Yeah, no, that actually is your most accurate answer.
Right.
So if I put that into a calculator and come up with that number, but you're going to have to round it off. There's no way you're going to be able to state it accurately. It's kind of like you leave answers with pi in them. You don't always
Okay.
round
This
pi
one
off
says
to
to
3.14.
This one says to correct to two decimal places, so I would do the math and just round it to
Yes.
the 100.
Yes,
Okay.
exactly. And your calculator will give you that. Now, be kind of careful. This is a really easy mistake to make. That is not equal to the natural log of 5.
No, it's not division. Natural division.
No.
Because n is a number.
If I had the natural log of 10 minus the natural log of 2, that is equal to the natural log of 10 divided by 2, which would be equal to the natural log of 5. So if I have that, that's equal to the natural log of 5. But if I have natural log of 10 divided by natural log of 2, I can't simplify that.
3.3219, blah, blah, blah.
Whatever it is. I don't care. But in other words, notice why it's easy to make that mistake. Those two things look a little bit similar.
Right, they do.
But they're not at all. In other words, you can only apply that rule of logs when you have log of something minus log of something else equals the log of their quotient.
Right. This is two separate logs.
Right. Exactly.
Okay.
All right, Max. Let's see. We have another session scheduled for Saturday at 10.
Yeah. Noon, my phone.
I will talk to you then.
Okay.
All right. Bye-bye.